developing this empirical formulas to determine the small whole number ratio in which these elements combine, which is Dalton's law of definite proportions.
And then lastly, we need to be able to
so using these percentages,
the
we can
empirical formula
compare
if we're given
them
data regarding the percent
to each other to determine what the ratio
of the
is
compound
between them.
All right,
We
so
cannot
first, the difference
compare
between an
masses
empirical and a
of
molecular
one to masses of the
is
other.
simply that the
That's like
empirical
comparing
formula
apples
is
to
the
oranges,
reduced
or what
form
in this
of the
case it's
formula.
comparing
So this is the
magnesiums
formula
to
that is
nitrogens.
reduced
So
to
we
the
have to convert
smallest
these
whole
to
number
moles, which is a
ratio
quantity that we can compare across
substrates.
elements.
And the
So the
molecular
first thing we
formula
need to do is
represents
convert
the actual
from
amount
these masses
of
to the moles.
of atoms
So
of each element that are present in the compound.
2 grams
So
of
in order
magnesium.
to illustrate the difference, we have a few examples
we're
down
going to look
here.
at our
H2O, since
periodic
we
table, because
cannot
we're going to
reduce
convert
this
from mass to
ratio to a
moles, so
smaller
that
whole
means that we
number
need to use our molar ratio, or our
empirical
molar
formula
mass.
for
So we look at
H2O is
magnesium, which is
also
24.31 grams.
Now this next
for
one,
1
I
mole.
see 2 carbons, 4 hydrogens, and 2 oxygens. These can be reduced to CH2O. Now, we can see that it's advantageous to write the molecular formula sometimes, particularly because as we're getting the hang of this, we can see that we can divide this by 6 and end up with CH2O, where these both have the same empirical formula. However, their molecular formulas are different, and in fact they are very different in structure and behavior, as this is acetic acid and then this is glucose. Acetic acid is not so great for us, where glucose is the fuel for our brain. So it's very important that we indicate the difference between these by writing the molecular formula of them so that we don't get confused when we are referring to either one or the other. Now, sometimes it is more advantageous for us to use the empirical formula. For example, ionic compounds form crystal lattice structures that are repeating, so it's better for us to just reduce these to the smallest whole number ratio in the empirical formula. All right, now back down to here, we take a look at these, and we can divide these by any number. However, we want our results to end up as a whole number ratio. Since 11 is a prime number, that means that none of these are divisible by the same number to give us a whole number. So the empirical formula over here is also C12H22O11. Perfect. So hopefully this gives us an indication of what the difference between a molecular and an empirical formula is. Then we can move down, and we're going to use this simple rhyme for a simple formula by Joel S. Thomson that was published in the Journal of Chemical Education in August of 1988. So if you go to the August 1988 edition of the Journal of Chemical Education, you can find this rhyme along with the rest of this document, except we're going to fill in part of the document so that we can have practice performing the calculations. So again, to give credit where credit is due, this was written by Joel S. Thomson and simply modified ever so slightly so that we can work through it as practice. So here is the rhyme. Percent to mass, mass to mole, divide by small, multiply till whole. Now we'll do that one more time just because it's so beautiful. It is percent to mass, mass to mole, divide by small, multiply till whole. That is such a simple yet eloquent poem that will help us when calculating the empirical formula of any compound when given the component percentages by mass. So our example problem is right here. A compound consists of 72.2% magnesium and 27.8% nitrogen by mass. What is the empirical formula? All right, so to begin with the first stanza, to break it apart, percent to mass. So what that means is that we need to convert our percentages to some mass. It really doesn't matter what mass we choose. It could be 7, 14, 21, or 3 trillion. But since these are percentages per cent out of 100, cent meaning 100, it would be much easier for us when we're doing the calculations to just say that the entire compound has a mass of 100 grams. So if the entire compound has a mass of 100 grams, that would make, since this is per 100, that would make 72.2 grams of magnesium and then 27.8 grams of nitrogen. Perfect. So now we've converted our percentages to masses of a comparable amount. Now, the second stanza, mass to mole. Since we cannot compare grams of magnesium to grams of nitrogen, we need to convert these to a quantity that we can actually compare, that are comparable. This is like comparing apples and oranges, and in fact, this is comparing magnesiums to nitrogen atoms. So we need to convert these to a quantity that we can compare them with, and in fact, the mole is that quantity. It's designed for that purpose. So we need to convert from mass to moles. So when converting from mass to moles, we're going to take the given, which is 72.2 grams of magnesium, put it into our conversion tool. Now diagonal across, since we're going from mass to moles, we look up our molar mass of magnesium, which right here is 24.31. So we put 24.31 grams of magnesium for 1 mole of magnesium. That'll give us what we're looking for. So let's pull up our calculator. 72.2 divided by 24.31 gives us 2.96999. So per sig figs, we would end up with, grams cancel, we end up with 2.97 moles of magnesium. Next, we're going to do the same thing for nitrogen. Nitrogen, we start with 27.8 grams of nitrogen. Put our molar mass to convert to moles. We have 14.01 grams per 1 mole of nitrogen. So 27.8 divided by 14.01. There we go. Gives us a grand total of 1.98 moles of nitrogen. There we go. Now, second stanza, mass to moles, is now addressed. Now we're going to tease apart divide by small. Now again, I said the reason we convert to moles is so that we can compare these two. Now that we can compare these two, we can determine the molar ratio in which these combine. In order to do that, we're going to choose the smallest amount, which is nitrogen, 1.98 moles of nitrogen. We're going to divide each of these by the 1.98. So that means we have 2.97 moles over 1.98 moles. And then our second one is 1.98 divided by 1.98. This one's pretty easy. We can just say that that equals 1.00. The next one we have to plug into our calculator. 2.97 divided by 1.98 gives us 1.5. All right. Now, since this is our molar ratio in which they combine in. However, when writing a formula, we cannot use 1.5. We have to use a whole number ratio. So in order to get that, we are going to multiply until they're whole. We're going to pick the smallest number to multiply them by until we get a whole number. For this one right here, it's going to be 2, because 2 will give us 3. So we say 1.50 times 2 equals 3. And then for nitrogen, we have to, whatever we do to one, we have to do to the other. So we say 1.00 times 2 equals 2. So that means that our formula is Mg, 3, and 2. All right, hopefully this is helpful. Hopefully this helps wrap up our unit, and I look forward to wonderful scores on our test coming up. Enjoy.